Something that's not quite covered in this section of the book, but is covered in other textbooks, is the tangent plane. We can calculate this using the gradient vector. Also, something called a normal line. We can calculate this using a gradient vector. So remember that the gradient of f is a perpendicular vector to every smooth curve on the surface. It means if I were to draw a curve on my surface and then calculate the gradient vector at any point on that surface, the gradient vector is going to be perpendicular to it. So imagine any curve that I could draw on this surface, the gradient vector will be perpendicular to that. Which is great because that vector would also be perpendicular to any tangent line through a point on our surface. So our tangent plane can be calculated using a gradient vector made up of all the first order partials. And then this idea of something called a normal line. It's a line that's perpendicular to your surface. The vector parallel to that line comes from the gradient vector. So it's the vector that contains all of the first order partials. If we wanted to find a tangent plane and a normal line for the surface given here, we would first calculate the gradient vector. We would evaluate that gradient vector at some point, like the one that's given to us. To find the vector 2, 4, 1. That's the vector that we would use for the equation of the tangent plane. Remember, the tangent plane needs a perpendicular vector, so our perpendicular vector is the gradient vector. It also needs a point on the surface. We are given that point as 1, 2, 4. So we can come up with the equation of the plane by taking each component and multiplying it by the change in the variable. Whoops. And then cleaning that up. To get our final answer for the tangent plane. For the normal line, we can write that using the parametric equations for a line, where x is equal to the x value point plus the x component from our parallel vector times t. Y is equal to the y value point plus the y component from our parallel vector times t. And then z is the z coordinate plus the z component times t. So this would be the normal line. If we wanted to use this idea, using the gradient vector to find a tangent plane and a normal line for a function that's only of 2 variables, you might think, oh, same process, find the gradient vector. But notice that this gradient vector for f, it's only going to have 2 components. And our tangent plane needs a 3D vector as the normal vector. So what we can do is start by rearranging our function. Instead of having f of xy equals just an expression involving x and y, we're going to rewrite our function replacing f of xy with z. And then we're going to create kind of a dummy function where we subtract z to the opposite side so that we have 0 is equal to negative x to the fourth plus x squared minus y squared minus z. And what we have on the right-hand side over here looks like a function of 3 variables. We can call that f, capital F, function of 3 variables. And then we can find the gradient vector of that and use that as our gradient vector in each of the formulas. So if we found the gradient vector of capital F, that would look like negative 2x. Oh, why do I have x squared written twice? Whoopsies, my x to the fourth turned into a negative x squared. So we have negative x to the fourth plus x squared minus y squared minus z. Let's calculate our gradient vector there. So we'll have negative 4x cubed plus 2x for the x partial, negative 2y for the y partial, and negative 1 for the z partial. If we evaluate our gradient vector for capital F at 1, 1, that's like x equals 1, y equals 1. And in this case, there isn't a z to worry about, so we don't have to worry about what z would be. However, if there were to be a z, then you would have to calculate what z is. But there's no z to plug into, so we'll just plug in x equals 1, y equals 1. So we get negative 4 plus 2, or negative 2 in the x direction. In the y direction, we also get negative 2, and in the z direction, it's that constant negative 1. And so then we would just use this as the gradient vector for the tangent plane or the normal line, whichever one you're working on. So this is a shortcut that we can use to find normal lines and tangent planes. It works for functions of 2 variables with a small rearrangement, and it worked for functions of 3 variables very smoothly.